So I recently finished my PhD at Monash University under Kevin Modi, who talked earlier today. And I've started a postdoc at Nanyang Technological University in Singapore, and that's the work that I'll be talking about today. So basically, this is about modeling. Modeling is a problem that's ubiquitous in science, but I guess why do we care about this in particular? It's that if we have an accurate model that's efficient, we can use it to predict the future and adapt our behavior. So, for example, kind of like personal example would be something like the weather. You can look at the forecast provided by the Bureau of Meteorology and decide, do I wear something warm or something cool? Of course, though, it's well known that predicting the weather is a notoriously difficult problem, especially in Melbourne. So there's this kind of fundamental tension that is ever present in modeling, which is we can have a simple model that's not very predictive, or we can have a very complicated model that's difficult to deal with, but it might be more predictive. So you can have something like, say, it's hot today, therefore it'll be hot tomorrow as your model. So then what you have is something that has very little processing requirements, obviously, but predictive ability is next to nothing. On the opposite extreme, you could have something like trying to track all the air molecules in the atmosphere, which maybe has slightly better predictive ability, but it's utterly impractical. So really, in modeling, what we're trying to do is we're trying to fight this fundamental tension where we want to track everything that matters, but only the things that matter. So it turns out that if we restrict the problem we're looking at in a few ways, there actually is an optimal solution for general processes. So the constraints are we're looking at classical stochastic processes here, which have discrete time, a finite range of outputs. They're stationary and they're ergodic. So if we satisfy those constraints, we can construct something called an epsilon machine, which is not new at all. It's been known for a couple of decades now. And it's been epsilon machines have been used to study things like financial data. It's been used in neuroscience. But of course, this is a classical tool to solve classical problems. And this is a quantum conference. So what do we do to make this quantum? Well, there's two ways we can look at it. So one way is we can still be interested in classical problems, but use quantum tools to handle it. So there are quantum generalizations of these epsilon machines, these maximally efficient models, which have provably less memory requirements, even compared to these maximally efficient models. This is what my group at NTU really focuses a lot on. So for example, they're using this to get memory advantages in modeling rare events in financial data. So the other thing you can do, of course, is use your tools to study a quantum system. So one of the things that's been done is using classical tools to look at quantum systems. Phil actually talked about an example earlier today, which was trying to find non-trivial memory effects in quantum dots, and epsilon machines were used to do that. So this talk is concerned with the full quantum picture, where we're using quantum tools and we want to describe a quantum system. And I think we care about this for quantum energy because the types of scenarios we're looking at, things like harvesting light, charging a battery. In general, the real physical system you'll be dealing with will be quite complex, and you want to have the most efficient model possible when you're dealing with these. So to begin with, we'll talk about the classical theory. So the fundamental object in computational mechanics is a classical stochastic process. It's a sequence of random variables, which is bi-infinite. That means it's got an infinite past and an infinite future. And each of these random variables can take a set of outcomes in some alphabet x, which is finite. So we can think of this as some black box. We can see the statistics of the outcomes, but we don't suppose we know what's in the black box. A fundamental requirement that we need in order to actually say anything reasonable about them is this notion of stationarity, which is basically the idea that when we conduct our experiment, doesn't change the result of our experiment. And mathematically, it's just time translation invariance of these random variables in the process. So just recording the statistics would be one way to look at these problems, but that's not very efficient. What we really want to do is construct some kind of simpler model. So a hidden Markov model one can think of as kind of like a hypothesis as to what's inside that black box. So it consists of an alphabet of memory states and some transition matrices that define a Markov process. So one can construct, say you have a person you're looking at, and sometimes they're happy, sometimes they're sad, but you can't read their mind, of course. So what you can come up with is a hidden Markov model to hypothesize what's inside that black box and say maybe the thing determining whether they're happy or sad is the weather. And these transition matrices define the probabilities of it going from, say, rainy to sunny and then being happy as a result, or sunny to rainy, and observing them being sad. But of course, this is a very simplistic and ineffective model of a human brain. So we're really concerned with models that are effective. So in this slide, we show these epsilon machines, these maximally efficient models of classical processes. So in order to get them, we partition our process into its infinite history and its infinite future. So of course, the history has already happened. It's not random anymore. And then we have this future process, which is now conditional on the past. So a conditional probability distribution. The key simplification involved in this is that if two pasts have the same conditional future probability, why would we bother storing both of them? So that's what we do. You define an epsilon mapping, which basically takes your histories into equivalence classes. So say you have history x and history x prime. If they yield the same p of x given x, you map them into the same equivalence class. And then an epsilon machine is precisely a hidden Markov model whose memory states are equivalence classes of these histories, and they're provably minimal. But what did I really mean when I said minimal? So to be exact, they're minimal in terms of among all models that reproduce the statistics of the process exactly, they require the least amount of information to track the memory state of that hidden Markov model over time. So mathematically, this corresponds to the entropy of the memory stationary distribution, and this property requires ergodicity. So this is the classical statistical complexity of a process, which is defined in terms of its epsilon machine. And something also to note is that this complexity is always going to be less than the log of the number of memory states that you found in your epsilon machine. That's an upper bound. So that was the classical picture. What I'm doing is trying to generalize this to study quantum processes. So the toolkit that I'm using to do this is a bit like what Phil was talking about in his talk. So this is the process tensor formalism. So on this slide is essentially the kind of situation that it describes, where we have, say, we initialize an experiment by applying some kind of control. Then we leave the system to evolve with the environment for some finite period of time. The environment might have some memory, and we can apply control again, and then free evolution again, and so on, to have this multi-time experiment. So the key realization here is that these multi-time objects can be partitioned into two things. There's the influence of the experimenter, their control strategy, and then this process tensor. Both of these are, in general, things that can act at many times and can have memory, so non-Markovianity. So this is what we use to construct a computational mechanics theory for quantum processes. So what we've defined in this slide is a quantum stochastic processes. Basically, the idea is we have what we saw in the previous slide, but our experiment involves measuring the system at each time, which means that we get a set of outcomes. And that set of outcomes is a classical stochastic process. It's just like the outcome of each measurement. However, this classical stochastic process is governed by this process tensor that I was talking about before. The other thing is, because of the way computational mechanics works, we have to make this experiment infinite past and infinite future, which is a little bit mathematically ugly. As I talk about for classical processes, we have this idea of the process is just the statistics of the black box. So equivalently, we can use what's called a tomographic representation of a process tensor, which equivalently is also just the input-output statistics of that quantum process, and that's what determines our statistics in a way analogous to a classical black box. So we can do some of the same tricks that we did for the classical processes, although the mathematics turns out a little bit differently. So we can partition our process into the past and the future, but there's a little divergence here because of this inherent non-passivity of measurement in quantum mechanics. So we can't just have a set of outcomes that we list. We have to specify how we did the measurement. So instead of just an outcome history, we have a joint action-outcome history. And we can do essentially what's a kind of tensor contraction of that with the bi-infinite process tensor from the last slide. And that gives us a conditional future process, which is equivalent to the conditional future probability distribution in the classical case. Using this, we can define stationarity as essentially time translation invariance of these conditional futures. So, we can also have quantum hidden Markov models. So basically, this is something that everyone would be very familiar with already. It's just what's inside the black box is just what is our environment that we have no access to. So it's just a specified dilation of a process is the equivalent of a classical hidden Markov model. So now we can actually construct the analog of these epsilon machines. So we play essentially the same trick, but just with our quantum objects. So we say if we have history A and history A prime, if they lead to the same conditional future process, then we group them into the same equivalence class, and we don't need to think about both of them independently. And then a Q transducer is a hidden Markov model, in other words, a unitary system memory dilation whose memory states correspond to these equivalence classes of action-outcome histories. And this is the basis of a paper that I'm currently writing up and should be on arXiv soon. So complexity is something we talked about in the classical case. You can do mostly the same thing for quantum mechanics, but there are some extra complications that one has to deal with. So in particular, I talked about this idea of the non-passivity of quantum measurement, which forces this to be slightly different. So to recall, the statistical complexity is the quantity of information that's needed to track the memory state over time. And we can define the quantum statistical complexity of a process, but we see it's not just in terms of the process tensor T, it's also in terms of this control strategy A. And that's sort of a fundamental fact that we can't get information from a process without actually measuring it, and we have to specify how we measure it. Of course, there is a way to sort of get around this, and this is just to maximize over all possible control or measurement sequences. And so we get this hierarchy of the complexity for a particular choice of actions is less than the maximum of all choices in the set you choose, which is always going to be less than the log of the dimension of the memory Hilbert space. And finally, I want to end on sort of getting back to why we actually care about all of this. We want to have efficient models of processes so that we can efficiently make decisions and predict the future. So we have this problem of synchronization, which is basically, it comes from the fact that, say we've learned this Q transducer, this efficient model of a quantum process. If we were to perform some kind of experiment that would allow us to know what that hidden memory state is, then we would have effectively a kind of maximum predictive ability given that process. So we want to be able to do that because that will enhance our ability to do things like charge a battery or harvest light or whatever else. So a result in this paper that I'm releasing soon is a synchronization theorem, which states that for all stationary quantum processes, there exists a control strategy that will induce synchronization of its Q transducer asymptotically. And that's all. Thank you.
Sure. There's a mic coming.
Thanks. That was fascinating. This last result reminds me of something in stochastic control theory, which, while not doesn't have the status of a theorem, is pretty well understood, and that's the optimal or good controller ansatz, which says that if you have a stochastic system out there in the world that you're trying to control, the best controller for it is a replica of the system itself. It seems like perhaps that's a relevance here to this notion of synchronization.
Yeah, I'm not quite sure how that would fit in, but I think there is quite a lot of subtlety to do with this question. So the version of this theorem that I've actually proved is quite a weak version of the statement. So I'm saying there exists a control strategy, not guaranteeing that no matter what you do, you'll eventually learn the final state. I'm also saying not any arbitrary model will synchronize, only the Q transducer will synchronize. At least that's the only thing I've proved synchronizes. And not that it will happen in a finite time, just that it'll happen eventually given an infinitely amount of time. I have a strong suspicion that if you want to prove something more constrained than this, in particular, if you want to have synchronization in a finite time, you might actually find that the problem is undecidable. So there's some work on this kind of stochastic control theory, this idea of quantum observable Markov decision processes. There's a paper by Scott Aronson which basically says that the classical version of this problem is is decidable, but the quantum version is undecidable. So the problem they talk about is the goal reachability problem, goal state reachability problem, which is very similar to this. Yeah, so there's quite a bit of subtlety here.
There is no quantum optimal control theorem so far as I'm aware.
Yeah, the Scott Aronson paper has some quite interesting results. Yeah.